Hello guys, in this video we will learn how do we backpropagate in RNN networks, recurrent neural networks. This is also famously called as backpropagation through time, okay, because we have multiple time steps. At each time steps we share the same weights Wx, Wa, Wy, right? So that's why we call it as backpropagation through time. So before actually getting into backpropagation, we will just revise quickly how we did forward propagation, okay? So this is how a basic neural network, a recurrent neural network looks like. This is just a block of RNN and this xt is input at time step t, at is activation at time step t, y hat t is output at time step t, and at minus 1 is activation at time step before time step t, that is t minus 1 time step, right? And whatever you see these small circles within this block, these are all hidden neurons. So if you treat this as a hidden layer, these are all number of neurons in the hidden layer, okay? So this is how a basic RNN network looks like. You already know this while I explained RNN forward propagation in my earlier video, okay? Now if I just unfold this, or you can call it as unfold or just expand it across multiple time series starting from first time step, okay? So this is how the recurrent neural network looks like. So don't get confused with multiple blocks. This is just one block replicated at different time steps, okay? So that's why we see the same weight metrics which are getting shared across multiple time steps here, okay? Same WA, WX and WY, okay? Hope these concepts are clear. If these concepts are not clear and how the forward propagation works, please go back to my previous video where I have explained forward propagation clearly, okay? So now I'll write the equations which are with respect to forward propagation. So what are those? I have the activations at is equal to some activation function, correct? WA at minus 1 plus Wx xt plus b a, right? And similarly for predicting the output at time step t, we will have some activation function applied on top of wy into at plus by, okay? So these two are the equations which we learned in our forward propagation, okay? Now this we can call it as output or total output, okay? Just remember this, okay? Let's not worry more about that. So these two equations we already have seen in my previous video where I have done forward propagation. Now what we do, we need to define some cost function, or you can call it as loss function, okay? So where we compare the output at time step t with our predictions at time step t. And for individual time step, let's represent it as L of t, loss at time step t, loss at time step t, okay? So our overall loss, let's represent it as L. It will be summation over multiple time steps, t equal to 1 to capital T, L of t, right? So this will be our overall loss function, and our aim should be to minimize this loss. It should be minimized. We should have minimum loss so that our recurrent neural network learns the task that we intend it to learn, alright? And how do we do this? How do we minimize this? We do forward propagation. We calculate the loss and we update these weights. What are those weights? WA, WX and WY, right? We also update the biases, but for this video, let's just concentrate on weights in order to understand backpropagation in a clear way, okay? And I'll explain you taking one of these as examples. How do we update WAs, okay? You can connect the same things with WX and WYs, okay? Now, so how do we update these weights? So it's the same process, right? So if you take gradient descent as our algorithm, we update the weights as WA is equal to WA minus alpha into DL by DWA. Correct? So what is this alpha? This is our learning rate. Okay, so this is called as learning rate. So now that we have this equation, we need to know what this derivative of loss with respect to WA is. Okay, now this is what is the most important step in our back propagation. Okay, so at any time step t, derivative of loss at that time step t with respect to WA. Okay, this can be written as derivative of loss with respect to t. Okay, derivative of loss at time step t with respect to the predicted value, that is y hat, at time step t, and this y hat t in turn depends on the activation at that particular time step, right? DA t, correct? And this activation at that particular time step depends on this particular weight WA, right? Hope this is clear. So how we arrived at this equation? We arrived at this equation with the help of chain rule. So I have also explained what is chain rule and how this is applicable in back propagation in my earlier video, where I have explained the chain rule with the help of simple computation graph with a simple algebraic equation. If you haven't watched that video and you are not clear how I arrived at this equation, I would suggest you to go back to that particular video. I will provide the link for that video in the description. Okay. So now we know that this is our equation in order to find this particular term here. Okay, now this is straightforward. We can get to know this because this is a loss at that particular time step with respect to the predicted value at that particular time step. The most important thing here is this particular candidate here, this one, okay, and specifically this one. These two are our most important derivatives. Okay, now let us see what is this DAT with respect to WA. Okay, so what I will do, I will say derivative of activation at time step t with respect to weights A, WA. So what is this? This is not just only one term. This is not just only one single term. Okay, so this is something else. This is actually a huge fella. This includes multiple components with it. Okay, so in order to explain that, let me just tell you some information on the time steps and activations. Okay, so let's say we have multiple time steps unfolded into this structure. Okay, so let's call this as A1, call this as A2, call this as A3. Like this, we will have AT minus 1 and finally we have AT. Okay, so these are all connected together and these are all governed by WA, weights, right, associated with our activations, WA, correct? Now if you look at this, AT gets T1, AT minus 1 as input, AT minus 1 gets AT minus 2 as input. Likewise, A4 will get A3 as input, A3 will get A2 as input, A2 will get A1 as input. And in the beginning of the time steps at time t0, we also have something called as A0, which is vector of all zeros. So we are not bothered about this particular time step as of now. We will not do any derivations with respect to this particular time step. Okay, we will consider and back propagate till A1 time step. Okay, now we have seen this particular thing here, right? So what I can do, I can write DAT with respect to DWA as DAT derivative of activation at time step t with respect to, this is our input to that, right? A t minus 1 is our input, correct? And this DAT1, the activation at time step t minus 1 is in turn dependent on DWA, correct? And further adding DAT, this is also dependent on DAT minus 2, right? This is dependent on all the stuffs, right? Back, because some information from first time step will flow till the last time step activation, right? This you have to remember and understand. And this DAT minus 2 is in turn dependent on DWA, correct? So this goes on and on and on up to DA2 with respect to DA1 and DA1 with respect to DWA, right? So this is what actually this particular term here is. DAT with respect to DWA. Okay. So this is a long computation, right? So we can represent this in a short way. So how we can do that? We can write it as DAT with respect to DWA can be written as, it's the summation of what things? DA and with respect to WA. Now we have to plug in t minus 1 so that it will be generalized. So how we can do that? I'll say some variable j is equal to 1 to t, okay, and what I'll say DAT DAJ, okay. Now if you expand this, whole thing, you will get this particular equation. Okay, so hope this is clear. So this is how we back propagate in order to find out the derivative of activation at time t with respect to weights A. Okay, now is this all? No, right? So recurrent neural network is not that simple, correct? This fella here, this guy here is actually product of multiple stuffs, right? As I have explained to you here, for t, input is t minus 1, t minus 1 is dependent on t minus 2, t minus 2 is dependent on t minus 3. Likewise, if we come till A4, it is dependent on A3, A3 is dependent on A2, A2 is dependent on A1, because preceding activations are inputs to our succeeding activations, correct? So that's how we compute the activations in recurrent neural networks. So let me just expand this guy here, DAT by DAJ. Okay, so what does this mean? So if we expand this, we will get derivative of t minus 1 with respect to derivative of, okay, so before I go on expansion, let me just write this in a better way. Okay, so this is derivative of activation at time step t with respect to, let's take j is equal to 1 for now. Okay, so this is DA1. So how do you calculate this? So this is a product of multiple things, right? So this is nothing but derivative of activation at time step t with respect to A1 can be obtained as derivative of activation at time step t with respect to t minus 1, derivative of activation at t minus 1 with respect to activation at t minus 2. So like this, we will go on and on. Derivative of A3 with respect to derivative of A2, derivative of A2 with respect to derivative of A1, correct? So here we end it here. So this particular thing, it's a product. It's a huge product, right? If we have a big statement with, let's say, 100 or 200 inputs, sequences or tokens, this will be multiplication of all those 100 or 200 tokens derivatives with respect to the activations. Okay. So, and if you look at this, these are all derivatives of activations, correct? Derivatives of activations. And what are these activations? These can be anything from sigmoid to ReLU, or it can be tan H, it can be softmax, it can be leaky ReLU, it can be ELU, it can be something called as max out. So there are multiple activations, right? So it can be derivative of any of these activation functions which we choose to be applied at that particular recurrent neural network. Okay. So guys, this is how backpropagation works in recurrent neural network. This is bit complex, but if you have good grip with chain rule, you can solve almost any derivatives like this. Okay, so it's simple. Now that I have told you how do we calculate this particular thing here, similarly we will have these updates. Now we had updates for WA, right? Similarly we will have updates with WX. What are those? WX minus alpha into derivative of loss with respect to Wx, and we have another thing Wy. It will be updated as Wy minus alpha into derivative of loss with respect to Wy, right? So now if you are interested and if you can take this as an assignment from my side, you can comment out the solution for these two terms. Okay, derivative of loss with respect to weights x, derivatives of loss with respect to weights y. Okay, so you can refer this how I derived for this particular term here. You can follow the same steps and arrive at these two particular derivatives. Okay, so once you do that, please comment that out so that others can also get involved in the discussion, and I will also let you guys know whether you have arrived at the correct equations or not. Okay, so hope you guys liked this video. I have tried to explain this in much simpler terms, as simple as possible. If you still have any questions, you can reach out to me and ask me any questions on comments. Okay, so if you like the content, please give it a thumbs up and subscribe to my channel if you have not subscribed yet. Till we see in the next video, see you. Happy learning. Bye bye.